So in the last class, we have discussed the general wave behavior along uniform guiding structure, the behavior of TEM waves and TE waves or TM waves along uniform guiding structures having arbitrary cross section. So we have discussed the general equations, and now here we are going to get or solve those expressions for rectangular waveguides having a rectangular cross section. In the previous section, we have seen a parallel plate transmission line, so which also act as a parallel plate waveguide because in addition to TEM waves, it can allow TM and TE waves to pass through. But there will be fringing fields at the edges of the parallel plate waveguide, and the electromagnetic energy will leak out through the sides of the guide and create undesirable noise to other circuits and system. So therefore, the practical waveguides are usually uniform structures of cross-section of enclosed variety. Simplest of such cross-sections are rectangular waveguides and circular waveguides. But the rectangular waveguides are more commonly used in practice than circular waveguides. So here we are going to study in detail of rectangular waveguides. So this is a rectangular waveguide. So the cross section is rectangular in shape, and we can see that it is a single conductor waveguide, and we have noted that TEM waves cannot exist in a single conductor, hollow or dielectric field waveguide. So there will be only TM and TE mode propagating along the rectangular waveguide. First of all, we discuss the TM waves in rectangular waveguides. So consider a waveguide like this. So this is having a rectangular cross section, and the sides are having dimension A and B. So this is the width A and this is the thickness B. So the length is infinite in extent, so which is along Z axis, and epsilon and mu are the constitutive parameters of the enclosed dielectric medium. And we have seen that for TM waves, the magnetic field is transverse to the direction of propagation, and HZ, the longitudinal component of magnetic field, is 0, and Ez is not equal to 0. And in the previous section of the general wave behavior along uniform waveguide, we have seen Ez, which is a function of x, y, and z, can be written as Ez0 e to the power minus gamma z, where Ez0 is a function of x and y alone, the transverse components x and y. And e to the power minus gamma z is a common factor for all the field components. So we have to find out only the value of Ez0. And from the previous section, equation number 3, we have seen that the Helmholtz equation can be written as del square xy z0 plus gamma square plus k square z0 equal to 0. So here we are writing only for Ez0 because for the TM wave Hz0 equal to 0. So we have to solve this equation, and we call this gamma square plus k square as h square. So del square xy Ez0 plus h square Ez0 equal to 0. So where del square xy is the Laplacian in the transverse directions, that is dou square by dou x square plus dou square by dou y square. So writing this in the Cartesian coordinate system, we get dou square by dou x square plus dou square plus dou y square plus h square Ez0 xy equal to 0. So since the waveguide is having a rectangular cross section, we use the Cartesian coordinate system. And now we have to solve the second order partial differential equation. Solving this equation, we can get the value of Ez0. So once Ez0 is known, we can find out Ez. Ez is Ez0 e to the power minus gamma z. And once the Ez0 value is known, we can find Ex0, Ey0, Hx0 and Hy0. Hz0 is already 0 since we are considering a Tm mode over here. So we're going to solve this expression. So in order to solve this expression, or in order to find the value of the unknown Ez0 of xy, here we use the method of separation of variables. So we assume that the solution Ez0 of xy can be written as some function of x into some function of y. Ez0 of xy is the product of a function of x and a function of y. Capital X is a function of small x alone and capital Y is a function of small y alone. So substituting this in this equation, we get dou square by dou x square, dou square by dou y square plus h square acting on x of x into y of y equal to 0. So first of all, we can find dou square by dou x square acting on x of x into y of y. So we are differentiating with respect to x. So y of y is a constant. Y of y into dou square by dou x square of x of x. So here x of x is a function of x alone. So we don't have to put the partial differential equation. The ordinary derivative is sufficient because capital X is a function of small x alone. So dou square can be written as d square by dx square of capital X. So you can put the argument if needed, small as a function of x plus. So now finding this, we can see that capital X of x is a constant and the derivative is also changed to ordinary derivative since capital Y is a function of small y alone plus h. So if you need it, you can write the argument also plus h square x of x y of y equal to 0. Now dividing each and every term with x into y, capital X into capital Y, x of x into y of y. So there is a y of y over here. So dividing this term, we get 1 over x of x into d square x by dx square plus x into x divided by xy. So that is 1 over y into d square y by dy square plus h square equal to 0. So you can put the argument if needed. Now we can take this term, first term, to the right side. Then we get minus 1 over x d square x by dx square is equal to 1 over y d square capital Y by dy square. So this is capital X and this is small x plus h square. So we can see that left side of this equation is a function of small x alone and right side is a function of small y alone. So since this equation should hold for all values of x and y, whatever be the value of small x and small y, this equation should be true. So this is true if and only if the both sides of the equation are separately equal to a same constant. So you must have seen these types of equation while solving the Schrodinger equation for hydrogen atom by the method of separation of variables. So this equation is true provided these left and right sides are separately equal to a same constant, a separation constant. So let me call this separation constant as kx square. So this is also equal to that kx square. So we get two ordinary differential equations. So LHS is equal to kx square gives one equation, and RHS is equal to kx square gives another equation. So LHS is equal to kx square gives this equation, and multiplying each and every term with capital X and rearranging the terms, we get d square capital X by dx square plus kx square capital X is equal to 0. So please remember that capital X is a function of small x alone. So this is our equation, and now we have to put the RHS is also equal to the same constant. So we get 1 over y d square y by dy square plus h square k square, and rearranging this we get 1 over y d square y by d small y square is kx square minus h square. So multiplying each and every term with capital Y and rearranging the terms, we get d square capital Y by d small y square plus h square minus k square capital Y is equal to 0. Now we call this h square minus kx square as ky square, and therefore this equation becomes d square capital Y by dy square plus ky square capital Y equal to 0. So let me call this equation as equation Roman letter 1, and this one as equation number Roman letter 2. Now we have to solve equations 1 and 2. So we have seen that this is equation number 1 is of the form d square capital X by dx square is some omega square x. So here omega is kx. So the solution of this types of equation is x is equal to, these are harmonic equations, and we know that the solution is a sin kxx plus b cos kxx. So we have to find out the constants a and b from the boundary conditions. So in the x direction, the boundaries are x is equal to 0 and x is equal to a. So at the boundaries, the electric field inside is equal to the electric field outside. The boundary condition should be satisfied, and the electric field outside is 0. So the boundary conditions are given by at x is equal to 0 and at x is equal to a, Ez0 equal to 0. So we know that this Ez0 is a function of x and y. So when we put x is equal to 0, we get Ez0 of 0 comma y equal to 0, and Ez0 of a comma y. So at these boundaries, x is equal to a and x is equal to 0, the electric field on left side and right side are same. Electric field on this side means just outside, which is 0, and here also like that. But we have seen that Ez0 is written as x of x into y of y. So x of x into y of y equal to 0 at x is equal to 0. And we know that along the x direction, y is a constant, and therefore we can write x of 0 equal to 0. Since equal to 0 at x is equal to 0, capital X at x is equal to 0 is 0, since y of y is a constant depending on the value of y. Okay. So similarly, from this expression we can see that x of a is also 0, because at this point also x into y equal to 0, y is a constant, and therefore x of a equal to 0. So applying these boundary conditions in our equation number 1, we get at small x is equal to 0, capital X is equal to a sin 0 plus b cos 0, that is a into 0 plus b into 1. So that is b. That is x of x at x equal to 0 is b. That is x of 0 equal to b. So substituting over here x of 0 equal to 0, we get b equal to 0. So our solution is x is equal to a sin kx alone, since b equal to 0. So the solution is given by a sin kx x. So now we apply the second boundary condition at x is equal to a. X of a is equal to 0. Capital X equal to 0 at x equal to a. So substituting as x is equal to a over here, we get x of a equal to a sin kx into a equal to 0. So this is true provided kx into a equal to m pi, where m can take values 1, 2, 3, etc. m cannot be 0. When m equal to 0, a is 0. But a is not 0 over here. So kx can be written as m pi by a. So the solution x of x, which is a sin kx into x, can be written as a sin m pi by a into x. A sin m pi x by a, where m can take values 1, 2, 3, etc. So this is the solution of equation Roman letter 1. So similarly, we can solve equation number 2. Equation number 2 is an equation on the variable y. So from this figure of the rectangular waveguide, we can see that y varies between 0 to b. So the boundaries are y equal to 0 and y equal to b. So solving this differential equation with the boundary conditions, y capital Y of 0 equal to 0 and capital Y of b is equal to 0. Then we can see that the solution is capital Y equal to some other constant a1 or a prime sin n pi y by b. So where n can take values 1, 2, 3. So in the above equation, we have chosen the integer as m. So here we have chosen the integer as n. And the solution is a prime sin n pi y by b. So where a prime is the amplitude. So now we have seen that Ez0 of xy is equal to capital X of x into y of y. So multiplying this, x of x is a into a prime sin m pi x by a into sin n pi y by b. Now we can call the products of those two constants as E0 another constant. So Ez0 of xy is equal to E0 sin m pi x by a into sin n pi y by b. So where m can take values from 1, 2, 3, etc. the integer values, and n can also take the integer values 1, 2, 3, etc. Therefore, this equation is the solution for the Helmholtz equation given by del square xy of Ez0 plus h square Ez0 equal to 0, or this equation. And also from this equation we have seen that h square minus kx square is equal to ky square. So from this equation, h square is equal to kx square plus ky square. So substituting the values of kx square and ky square from here. Kx is m pi by a And similarly, by solving this equation, you can see that ky is equal to n pi by b. So this is an assignment for you. And also, please solve this expression to get y of y is equal to a prime sine n pi y by b. Okay, so ky is here. So that is equal to n pi by b. So kx square is equal to m pi by a whole square plus n pi by b whole square. So this is the value of h square. So we have found z0 here, and for TM waves we know that hz0 and hz are zeros. Ez is ez0 multiplied by e to the power minus gamma z. So this multiplied by e to the power minus gamma z gives Ez as a function of ax, y and z. So knowing Ez0, we can find out Ex0, Ey0, Hx0 and Hy0 using these equations. But we know that for TM mode, Hz0 part 0, and therefore these equations 11, 12, 13 and 14 reduces to equation numbers 15, 16, 17 and 18. We have already discussed all those equations in our previous session, and substituting the value of Ez0 over here. Ez0 is equal to E0 sin m pi by a x into sin n pi by a into y. We get Ex0 of xy is equal to minus gamma by h square into m pi by a E0 cos m pi by ax into sin n pi y by b. Ey0 is equal to minus gamma by h square into n pi by b E0 sin m pi x by a cos n pi y by b. Hx0 of xy is equal to j omega epsilon by h square n pi by b E0 sin m pi x by a cos n pi y by b. Hy0 is equal to minus j omega epsilon by h square m pi by a E0 cos m pi x by a sin n pi y by b. So please get these equations by substituting the value of Ez0 in equations 15, 16, 17 and 18. So we got the values of Ez0, Ex0, Ey0, Hx0 and Hy0 for TM mode in the rectangular waveguide. And we already know that Hz0 is equal to 0. So here we know that gamma is the propagation constant. So we know that in terms of gamma, h square is written as gamma square plus k square. So the propagation constant gamma square is nothing but h square minus k square. So substituting the value of h square from here. So this is the value of h square for a rectangular waveguide. So h cannot take all the possible values. It can take only certain values. M pi by a whole square plus n pi by b whole square. And k square is k is omega root mu epsilon, and therefore k square is omega square mu epsilon. And gamma is the square root of this quantity, and from propagating mode gamma is purely imaginary, so root of this quantity. So we can take negative outside, minus of omega square mu epsilon minus m pi by a whole square minus n pi by b whole square. So root of minus 1 is j into root of omega square mu epsilon minus m pi by a whole square minus n pi by b whole square. And for propagating mode, we know that gamma is j beta, alpha 0. And comparing those two equations, we can get beta is equal to root of omega square mu epsilon minus m pi by a whole square minus n pi by b whole square. And here we know that m can take any integer values 1, 2, 3, etc. up to infinity, and n can also take integer values. So the combination of integers m and n defines a possible mode that is designated as Tm with integers small m and n. So when m is equal to 1 and n equal to 1, this represents a Tm 1 mode. Okay, so therefore there are infinite number of Tm modes. So since there are infinite values for m and n, there are double infinite number of Tm modes, because m can have infinite number and n can have infinite number. So there are different combinations for m and n. And we know that m is there in the expression E0 sin m pi x by a, and n is there sin n pi y by b. So when m is 1 along x direction, the wave is like this, 1. So you have plotted all these figures in the case of a particle in a box, right? When n equal to 1, this is a wave like this. M equal to 1, this is a wave like this along x direction. And when m is 2, this is a wave like this. When m equal to 3, there are 3 half cycle variations. So the first subscript m here denotes the number of half cycle variation of the field in the x direction, and n denotes the number of half cycle variations of the field in the y direction. So when n equal to 1 and the y direction, there is only one half cycle, and when n equal to 2, there are 2 half cycles, and like that. So this is the value of the propagation constant gamma, and we have seen that the cutoff frequency of a particular mode is a condition at which the propagation constant equal to 0. And propagation is possible for frequencies above cutoff frequencies. So the cutoff frequency is defined at the point where gamma equal to 0. When gamma equal to 0, then the quantity omega square mu epsilon minus m pi by a whole square minus n pi by b whole square is equal to 0. So omega square mu epsilon is equal to m pi by a whole square plus n pi by b whole square. Omega square is this, and therefore omega is 1 over root mu epsilon root of m pi by a whole square plus n pi by b whole square. So this happens, the propagation constant equal to 0 only at the cutoff frequencies. Therefore this is the corresponding cutoff frequency omega c. Cutoff angular frequency omega c. The corresponding cutoff frequency is omega c by 2 pi. So we can take pi out of this. There is a pi square over here and pi square. So we can take pi square as a common factor. So taking pi square out of the root, we have a pi over here. So this pi and the pi in the denominator cancels, and we have the corresponding cutoff frequency equal to Fc equal to 1 by 2 root mu epsilon into root of m by a whole square plus n by b whole square. It depends on the indices m and n, and therefore this is the cutoff frequency of a Tm Mn mode. The corresponding cutoff wavelength lambda c is equal to u divided by Fc. U is 1 over root mu epsilon divided by Fc. So substitute the value of Fc, we get the cutoff wavelength lambda Cmn is equal to 2 by root of m by a whole square plus n by b whole square. So here also the cutoff wavelength depends on the indices m and n. And we can see that for TM modes in rectangular waveguides, neither M nor N can be 0. So this cannot have a value equal to 0, because when M and N are zeros, we can see that the EZ0, which is equal to E0 sin M pi x by A sin N pi y by B. So when M equal to 0, EZ0 is 0. And when n equal to 0, this is 0. When m and n are both equal to 0, this is 0. So, ഏതെങ്കിലും ഒന്നിന് പോലും 0 എന്ന വാല്യൂ എടുക്കാൻ പറ്റില്ല. കാരണം EZ0 0 ആയി കഴിഞ്ഞാൽ നമുക്കറിയാം ഇതൊരു TEM വേവ് ആയിട്ട് മാറും. ഓൾറെഡി നമ്മൾ അസ്യൂം ചെയ്തിരുന്നു XZ0 is 0. When EZ0 is also 0, then that does not correspond to a TM wave. It will be TEM. So for a TM mode, neither M nor N can be 0. And the lowest value of cutoff frequency is when M equal to 1 and N equal to 1. So the lowest value of M is 1 and that of N is 1. So when M1 and N1, the cutoff frequency is minimum. So we can say that TM11 mode. TM11 means TM mode with M1 and N1 has the lowest cutoff frequency of all TM modes in a rectangular waveguide. For propagating mode, that means when the frequency is greater than cutoff frequency, the phase constant is equal to k into root of 1 minus fc by f whole square. The same value phase constant we have derived for a general waveguide. So the expression for beta and the wave impedance ZTM are same as that of the general waveguide. So we can apply those expressions for phase constant and wave impedance for a general waveguide in the case of a rectangular waveguide, also for TM mode, propagating TM mode, where the frequency is greater than the cutoff frequency. Now we discuss the TE modes in rectangular waveguides. And we know that for TE waves, EZ equal to 0 and EZ0 is also 0, and HZ is not equal to 0. So HZ as a function of x, y and z can be written as xz0, which is a function of x and y alone, into e to the power minus gamma z. And the corresponding Helmholtz equation for hz0 is given by dou square by dou x square plus dou square by dou y square plus h square, hz0 xy equal to 0 over h square is equal to gamma square plus k square. And the solution for hz0 should satisfy the corresponding boundary conditions. We know that the boundary conditions are the conditions to be satisfied at the boundaries, and we know that the tangential component of electric field is continuous across the interface. So for TM modes, we have applied the boundary condition for the tangential component of electric field. So at x is equal to 0 and at x is equal to a, the electric field is equal to 0. The electric field just outside the boundary. And also at y equal to 0 and y equal to b, the tangential components of the electric field are zeros. But in the case of TE waves, we have a second order partial differential equation for hz0. So the corresponding boundary conditions should be written in terms of xz0. And we know that the x is equal to 0 point is the yz plane. So the tangential component is either the y component or the z component. So here we consider the y component. So Ey equal to 0 because the z-axis is infinite in extent. So we consider the y component. So at x is equal to 0, the electric field along y direction should be 0. And at x is equal to a also, which is also the yz plane, Ey should be 0. But for a transverse electric wave, we know that Ez zeros are zeros, and therefore the equation numbers 11, 12, 13 and 14 becomes this. So from this we can see that Ey equal to 0 implies Ey0 equal to 0, which is equal to j omega mu by h square dou hz0 by dou x. So when Ey0 equal to 0, that implies dou hz0 by dou x is equal to 0. So this is being a constant. So therefore dou hz0 by dou x is equal to 0 at x is equal to 0 and x is equal to a. So this is the first boundary condition, and the second boundary condition at y equal to 0 and y equal to b. So at y equal to 0 means xz plane, the tangential component is ex, and at y equal to b also, it is also a plane parallel to xz plane. So the tangential component is again ex. So ex is equal to 0 at y equal to 0 and y equal to b. Ex0 means the corresponding ex0 is also 0, because ex is ex0 e to the power minus gamma z. E to the power minus gamma z cannot be 0. And from this equation for TE waves, we can see that when ex0 is equal to 0, dou xz0 by dou y is also equal to 0. So we can have at y equal to 0 and y equal to b, dou xz0 by dou y equal to 0. So this is the second boundary condition. So applying these boundary conditions for the solution of the Helmholtz equation in hz0 by the method of separation of the variables. So we have done the same procedure in the case of TM waves. So here also the same procedure is there, but the only difference is that the boundary condition is for the derivative. So in the previous case, the boundary condition is for the electric field, and here the boundary condition is not for the magnetic field, but the derivative of magnetic field. So that is the only difference. So the since this is for derivative, the corresponding solution for hz0 is given by hz0 of x comma y is equal to h0 cos m pi x by a cos n pi y by b. So since the boundary condition is for the derivative, we can see that the corresponding functions are cosines. So please find out x of x and y of y separately, and applying the boundary conditions, you can see that hz0 is this. So this is an assignment for you, and we have found out the value of hz0, and ez0 is already 0 for TE waves. And once hz0 is known, the other field components ex, ey, hx and hy can be found using those equations by substituting the values of hz0. And therefore we can get the values of ex0, ey0, hx0 and hy0 for TE waves in a rectangular waveguide. So which are given by those equations. So these equations are just obtained by substituting the value of hz0 in those equations. Okay, so please verify this also. And the value of gamma is same as that of the TM mode. We have already derived the value of gamma for TM mode, which is j beta is equal to j into root of omega square mu epsilon minus m pi by a whole square minus n pi by b whole square. And also we have found the cutoff frequency for that case. So this is the cutoff frequency of a TM mode. The same equation is true for the cutoff frequency of a TE mode. So the propagation constant and the cutoff frequencies are same for both TM mode and TE mode for a rectangular waveguide. And since these are cos functions, we can see that either m or n can be 0 here. So if m is 0, hz0 is h0, cos 0 is 1, h0 cos n pi y by b. So it's a function of y alone. When n equal to 0, hz0 is equal to h0 cos m pi x by a. It's a function of x alone. So either m or n can be 0, but both are simultaneously not equal to 0. When both are equal to 0, this hz0 is equal to h0 into cos 0 into cos 0. So that is h0 into 1 into 1, h0 itself. So hz0 is a constant when both m and n are zeros. But when hz0 is a constant, all the field components which depends on the partial derivatives of hz0 will be zeros. Once hz0 is a constant, these are all zeros. hx0, hy0, ex0, ey0 are zeros. And for t mode, we know that ez0 is already 0. So all the components other than hz0 are zeros, and hz0 is a constant. So this configuration is not possible. So in a TE mode, either m or n can be 0, but not both. Simultaneously m നും n നും 0 ആവാൻ പറ്റില്ല. ഒന്നുകിൽ m ന് മാത്രം 0 ആവാം, അല്ലെങ്കിൽ n ന് മാത്രം 0 ആവാം. And we know that the cutoff frequency for the rectangular waveguide, whether it is Tm or Te, is given by 1 over 2 into root of mu epsilon into root of m by a whole square plus n by b whole square. So this is the cutoff frequency. So now we have to calculate the lowest cutoff frequency. So we can have two configurations, m equal to 0, n equal to 1, and n equal to 0, m equal to 1. So, and we will check which one correspond to lowest cutoff frequency. For when m equal to 0, n equal to 1, this corresponds to TE01 mode, and the cutoff frequency of the TE01 mode is 1 by 2 root mu epsilon. Since m is 0 here, we have n by b whole square. Root of n by b whole square is n by b itself. But n is 1, and therefore we have 1 over 2 root mu epsilon 1 by b. 1 over root 2 mu epsilon, 1 over root mu epsilon is the u, and this is u divided by 2b. And the cutoff frequency of TE10 mode can be calculated like this. And here we can get that the cutoff frequency of TE10 mode is u by 2a, where u is the velocity of the electromagnetic wave in the unbounded dielectric medium. And for this configuration, we can see that a is greater than b, and therefore, so the reciprocals are inversely related. U by 2a is less than u by 2b. So therefore, the TE10 mode has the lowest cutoff frequency when a greater than b. A is the dimension of the rectangular waveguide along x direction, and b is the dimension of the rectangular waveguide along y direction. So a act as the width and b act as the thickness. So if a greater than b, then the FC cutoff frequency of the TE10 mode is the lowest. When a is less than b, then u by 2b less than u by 2a. That is the cutoff frequency of the TE01 mode is the lowest. And the mode with lowest cutoff frequency is generally termed as the dominant mode. And therefore, TE10 is the dominant mode of a rectangular waveguide with a greater than b. And TE01 is the dominant mode of a rectangular waveguide with b greater than a. So for most of the rectangular waveguides, a is greater than b, and TE10 act as the dominant mode of the rectangular waveguide. Okay, thank you.